duda que tengan, al final en español y se les respondemos.
En el evento también, si gustan, y si en inglés no vienen mucho, igual lo podemos comunicar y tratamos ahí de resolverlo. Okay, so Brian, his name, Brian Powell, VP, Vice President from Precise Automation, is the name of, es el nombre de esta marca.
So, what I'm going to present on today is collaborative robots. Collaborative robots are different than regular robots in that collaborative robots are meant to be used or work around people and not be guarded in a safe enclosure. So first, this is my plan today in terms of what we are going to talk about. A little bit about our company. I'll also talk about what's happening in the world of robotics, and then I'll also speak about the regulations that decide what a collaborative robot is supposed to be, and then we'll talk about what we do differently in terms of cobots, and then eventually I'll turn on the robot and you'll be able to interact, be able to play with the robot a little bit. Okay? So, our company, Precise Automation, is based in San Jose, California, Silicon Valley. These two gentlemen are Brian Carlisle and Bruce Shimano. They're our founders, and they have been in the robotics industry for maybe over 40 years. They've been making, building, and researching robots for many, many years. They met at Stanford. Their story is very typical of entrepreneurs in Silicon Valley. Meet in college, meet in university, come up with a great idea, and then make a company. And so that's what they did many years ago. In fact, they have the first robot they ever designed is actually in the Smithsonian Museum in Washington, D.C. So they have been designing robots for many, many years. So our robots are actually built in Southern California, in a city called Tustin, which is essentially very close to Disneyland, actually. So our company, the way that we work is we are mainly engineers, and then our partner in Southern California builds our robots for us. This helps keep our costs down, and it also helps us to make changes to our robots very quickly. It makes it very flexible. I think it's important to mention, actually, we are profitable, we're cash flow positive, and we're growing and have been. It's actually now 7 years. So our business, I think, is growing and doing very well because of collaborative robots are very popular right now. Seems a lot of people are talking about them. So, why are robots so popular these days? Well, if you can see the graph okay, I'll point out using my mouse, hopefully. Let's see, figure out how to get over there. There we go. If you can see my mouse, this red line, red solid line, is the cost of big robots. This is, the blue line is essentially the cost of small robots. And if you look closely, you can see that the cost of labor in, for example, Germany, very, very high. Cost of labor in the US is also very high. But this is the cost of labor in China. And as you can see, the cost of labor in China is going up and up and up. Now, this has an interesting effect in that if you look at the number of robots being used around the world and what countries are buying the most robots, it used to be that China didn't buy very many robots. In the last 2 years, China has passed everyone in the world, and they are buying more robots than any other country in the world, even though their labor is still very, very low cost. And so I think that they have figured out that robots, you can see here, the cost of a small robot, like this robot, is less than the cost of a worker or 2 workers on 2 shifts per day over a year. The robot ends up being less expensive than their labor. So they're now looking to automate very much. In fact, many companies in North America are now starting to bring manufacturing from Asia back to North America. So it's a very interesting trend because of automation and because of robots. So I'm going to skip this slide very quickly. So this is actually the forecast for use of robots worldwide. And if you look carefully, you can see that most of the lines are pretty straight. They're just kind of moving along nice straight lines. And then there's this one line that looks like it's going crazy. And that one line that is going crazy right here is China. And you can see what happened. Right about the time that they figured out that the cost of labor was high, or that robots were cheaper than labor, they started buying lots and lots and lots of robots. And so at this point, we believe that if a company isn't already thinking about robots, they're falling behind by not using robots. Because China, even though they have really low labor, is already, they've already figured out they're going to automate in a very big way. Robots are forecasted. This is the supply of industrial robots. They will continue to grow over a very long period of time. And the use of robots is just simply going to continue to increase. If you look at the robotics market in terms of Asia, Europe, and Americas, Asia is obviously growing very, very fast. And what's interesting is, actually it shouldn't say the US, it should say that North America, if you count the United States, Mexico, and Canada together, it's the 3rd largest robot market in the world. So I think that is possible for us to actually have small parts manufacturing and to have collaborative robots make a big difference in our manufacturing, rather than having manufacturing leave North America and go to Asia. Now, typically, small parts manufacturing has been done by hand, and due to changes in technology, robots are getting smarter and more capable. And so, as an example, this is an example of an alternator in a car part that weighs 7 kilograms, but it's made up of many, many small parts, all of which typically are touched by a robot, some are manufactured by hand. This example shows that just in terms of manufacturing using robots with small parts, it can be very efficient. Even though it's not part of the larger part may not be able to be handled by a robot, all the small parts can be. And that's part of what's driving the Cobot market to be the fastest growing part of the robot market. Now, what does it mean to actually be a Cobot? A Cobot is short for collaborative robot. And a collaborative robot, there's really a number of things that go into a collaborative robot. And I'll talk about first an example of a collaborative robot. This is a Kawasaki Robot, very, very big, very dangerous, but it has been made into a collaborative robot by putting a joystick and putting controls on the robot so that a human being can interact directly with the robot. Now, it still has to have safety guards around it, and it's obviously a very special way of doing collaboration. This is very complicated, I think, in terms of how a robot might be used for a collaborative robot. Really what you want to be able to do is to have a robot working and have people working around it. Now, if you watch this particular robot, this robot slows down when the person gets closer, and then it stops when the person is really close to the robot, so the robot can't hurt them. Because that robot is actually very big and very dangerous and can generate a lot of force. Now, you can see now as he backs away, using this special sensor, a laser scanner, it's possible for the robot to sense when a person's close. But the problem with this is that while it's safe, it means that the robot is actually not producing anything when a human being's close. So that really defeats the purpose, or the meaning of a collaborative robot. So what you really want is you want a collaborative robot to be something that it's limited in terms of how much force it puts out, and so it can't hurt you. But it can still do meaningful work, can actually do something useful for you. And so you can see in the example below that the robot can bump you, you can push it, it can even trap your fingers in here and it won't hurt you. And that's the idea behind collaborative robot. Now, the International Standards Organization, ISO, has a new standard, the 15066 standard actually defines what is a collaborative robot. And really, what it really defines is how much force can a robot be allowed to generate. And so the values that you see here are measured in newtons. And so if you look at where you might make contact with a human being, it's telling you, for example, the forehead, the amount of pressure that you can allow is 114 newtons, right? Versus, let's say, if you were to push on your temple's actually softer than your skull, right? So this has a value of 85, which means that you can actually, it takes less force to cause an injury. Really, the whole idea here is that the robotics institutes around the world have done a lot of testing, poking and hitting graduate students and university students, torturing them, really. And they tried to define how much force actually would cause injury. Now, in most new cars, if you roll up a window, and let's say a child's hand is in the window, if you roll up the window, what happens? In most new cars, the window stops and then goes back down. And that's exactly the same kind of technology that we're talking about here. The robot senses how much work it has to put in to close the window. The robot senses how much force it's actually generating and how much it's having to exert energy to do something, and it will stop if it takes too much energy. And that's the same idea behind the window in a car. It's the same idea behind, say, doors in a subway or an elevator. They all have this idea of limiting how much force gets generated so it doesn't hurt someone. And so the idea of collaborative operation it's been around for a long time. I don't know if they really had to torture all those people, but at least we know what the real numbers are. Now, the specification, it's important to understand the difference between the types of collisions that you can have with a robot because the values differ. So as an example, if this robot were just moving in space and it hit me, that would be a free space collision. And because I'm not trapped against anything, I can move if I get bumped, right? But you can see if my hand were on a table and the robot came down, then the only thing that's going to provide compliance is my hand, right? So that's the part where we really look very hard at how much force we generate, because that's the place where you can get hurt most easily. Now, what that means is that we actually use a force sensor. You can see here someone's holding the force sensor by hand, and the robot is hitting the sensor so that we can understand. Now this is a free space collision, so you can see that in free space it's somewhere around 65 newtons, which is really not much. It's like a small child hitting you. 217 newtons when you get trapped, that's a lot more force. And what's important to realize here is that our robots can actually move pretty fast and still keep the value or keep the force fairly low. You can see in the chart above how fast you can move and which part of the body you can hit, and it will generate very little force. Ultimately, the point of this is that there are a number of things that go into figuring out if a robot really is collaborative. One is how much force is the robot generating. Another important piece is how much compliance is there in the system. The robot has a certain compliance. You can see here I can move it just a little bit, yeah? So that's compliance. My hand being pushed is compliance. Actually, my hand being squished is compliance, right? And so you have to measure all these things. You take them into account, and that's what allows you to figure out, how easily or how hard it would be for someone to get hurt. Think about it this way. If you're driving in a car and you run into a fence and the fence can be knocked down, then there's much less force in terms of force being imparted. Versus if you ran into, instead of running into a fence that gets knocked down, what if you ran into a building and the building didn't move? Then the crash is much worse, right? Much more force, because there's no compliance, there's nothing giving way. And that's the idea behind understanding compliance when you're working with a robot. That's really what makes it, understanding the compliance is what really helps you make a collaborative robot. And so in this chart, and it might be very difficult for you to read, what it says here is that you can read in the chart, the highlight is for the upper arm, the lower arm, and then the hand and the finger. And if you look at the hand and the finger value, it's actually 75 newtons is what's allowable for what's called the compression constant, or how much force can be applied to a hand. So we use the hand as our way of measuring or testing whether or not our robot is compliant. And the reason for that is, what's the most likely thing to get near a robot, right? You're very unlikely to be sticking your head next to the robot, right? But if I were grabbing something, it's very likely that my hand might get trapped or hit, right? And so that's why we use the hand as our measure of what part of the body you might actually be getting hit. So we did do a lot of testing. Now this shows essentially testing in rigid situations. So this is the robot actually, coming down on something really hard. So if you had your hand in there, you would experience 150 newtons of force. Now, it won't break your skin. It probably won't, it won't send you to the hospital. It won't break a bone. It might smart. It might hurt. But no one said that collaborative robots are supposed to be painless. It might remind you that you probably shouldn't be, doing something with the robot in that way. But it does mean that the robot itself, it generates very little force compared to a big industrial robot. So as an example, a big industrial robot might generate 10 times as much force, 1,500 newtons of force, which would, not only break your hand, but it might, take it off. And you obviously don't want that. So, collaborative robots, our collaborative robots specifically, we have tested to make sure that they don't generate too much force. So if you can read this, there's a chart down below, and that chart down below here is, these numbers represent how much force the robot is creating or generating versus free space collisions and rigid surface collisions. And so what that means is that the robot is actually, we're proving the robot to be safe. Just, if I were to run this robot and move it around, all of you could come up and be near the robot, and it's impossible for it to hurt you. Now, that doesn't mean, however, you might not have an application where you could take the robot and not have it be safe anymore. So as an example, if you were let's say you were a knife manufacturer. Well, if you put a knife at the end of this robot, even though it generates just a little bit of force, that would make the robot not safe anymore, if you were picking up and putting down knives. And so you have to be, when you think about how to use a collaborative robot, you have to really think through how it might work. If someone was picking up something like, let's say, a printed circuit board or a telephone, a smartphone, then those things really aren't going to create a situation where it's not safe. But if you were, say, making needles for medical reasons, that wouldn't be a safe thing to have the robot. You have to protect people, and so there are a number of things that you have to think about when you're going to apply a collaborative robot. Even though the robot itself may be safe, the collaborative robot has to work inside of an environment, right? So let's say that I was doing something as simple as just handling these cosmetic jars. The thing is that I could still have something around the robot. Let's say I was putting these cosmetic shelves on some sort of shelf, right? And if I designed the shelves to be very, very thin, let's say like a sharp knife edge, then the robot could bump someone's hand into the shelf, and even though the robot is safe, that application isn't safe. So we worry a lot about how much does the thing that you're moving around, how much does it weigh? We worry a lot about what kind of collision it is, how much compliance there is in the system, but then we also worry about this last piece, which is how is the robot being used? What's the work cell design? Is it safe around the robot? Or is there something in the space where the robot's going to be working that could be a danger to a human being? So for most applications, most of you, I'm sure, would understand the equation for force, which is force equals mass times acceleration, right? So the more mass that you have, the slower the robot has to go, otherwise you're generating too much force. Make sense? And so if you look at a big robot like this one right here, it takes a lot of power, and it means that it can move a lot of mass, but it means that to be collaborative, it has to move very, very, very slow. And that's something that we do that is very unique. Our robots have very low gear ratios and low mass. And that's really the idea behind trying to make the robot collaborative. It has a benefit, though, a side benefit, which is our robots take very little power. This robot takes about 100 watts of power, as much power as you're taking just sitting here, right? So it's kind of like having a human being around, whereas a big robot, it takes like 1,000 watts to run one of those big robots. So over a long period of time, you would have a cost savings in your factory, right? You have to think about things like robot payload. You also want to think about the design of the robot, and does the robot have low gear ratios or high gear ratios? Just like in a car, the lower your gear ratio is, really the less power you can generate, right? Versus at a really high gear ratio, you go really fast down the freeway, right? And so that's the idea here is that we try and use low gear ratios to keep our power low so that we don't hurt someone. And so I'm going to skip over this slide and go to, now there are things that you can do in terms of thinking through how to design a work cell, how this robot can be used in a work cell space. There are things that you can do from the perspective of making sure, since we already know that moving the robot around in free space is less likely to hurt someone, you can move fast, let's say, when you're not putting something down. But you can see here, when you're going to put something down, we would recommend that you go slower, right? Just so you don't hurt someone. Now, where you're going to put something down, it makes just logical common sense that you might use foam, or you might round edges, right? So you want to make it so that it's as safe as possible, so that if someone were to get their hand trapped between the robot and, say, the nest where you're going to put something down, if things were rounded, then it creates less pressure. Obviously, it's easier to get hurt doing this than doing this, right? Surface area matters. So you want to do that for not only fixtures and parts around the robot, but also for the pieces that are attached to the robot, the gripper. And so you would actually have you want to make sure that your gripper has either foam or rounded edges, no sharp points or sharp edges. Just common sense. So there are a lot of different applications for robots, and I'll talk more about what industries that we work in and also what applications might work best. But in general, the easiest applications are applications where the robot, all it has to do is pick something up and put it down someplace. And there's a lot of places inside of factories where people are just handling material. Whether it would be for medical devices, packaging, or it might be for PCB, where you're putting it into a tester and waiting for it to tell you it's okay, or consumer goods, where you might be assembling some parts together. So we make 3 different types of collaborative robots. We make a Cartesian robot, which just means that it moves on linear axes. We also make a Sphero robot, which is exactly what you're seeing here. And then we also make a 6-axis robot. And the 6-axis robot can move like a human arm. So it can be very dexterous. It can move around in very complex ways. So these are some examples of the safety of our robot. And I always like to show this one first, because this is actually our chief test engineer. Her name is Nina. You can see she's a princess. She's 6 years old. And the reason why we like to show this particular video is because she's the daughter of one of the chief design engineers. And so you can imagine that if the robot wasn't safe in every possible way, he probably wouldn't let his daughter close to the robot, right? So that's really the point here. Plus, she is a lot of fun and very helpful in the lab. So this is basically showing this robot, how safe it is. You can put your hand in here. You can push it. You can pull it. Get in the way of it. It's safe. We also have a 6-axis robot. You can can see it's very easy to just simply stop and run into the robot. And then the Cartesian, this is it takes very little force. If a 6-year-old tiny little girl can stop the robot, then a person on the manufacturing floor would be able to stop the robot. All of our robots have some very unique features about them. First of all, you'll notice that there isn't some big box anywhere around this robot. The robot is completely self-contained, and the controls, the electronics, are actually inside the robot. So you don't have to have a separate place to store electronics, which makes this very nice because you can mount this robot on a cart and push it around, and all you have to do is unplug it from the wall, move it, plug it back in, and then it's ready to go. It's a very nice feature. And that's true of all of these smaller robots, is that they have all the controls are actually built in. They're relatively small. You can actually pick this robot up and walk around with it. They all share the same way of programming, or the same way of making the robot do something useful. And I'll show you more of this in just a little bit. You can see here that there's a web-based interface. So Internet Explorer or Chrome or Safari, any of the browsers that you might use from a computing device, you can just simply put in the IP address of the robot, and that allows you to have access to configuring the robot and making it run programs and stopping it and that sort of thing. And then there's another interface here, which is our programming interface. It's really for advanced uses. Most of the time, people can just simply use our web interface, and that allows them to do useful things with the robot. Something else I did, this is just showing you the example of how the robot's very lightweight. You can pick it up, move it around, and it's very low power. Another interesting thing is that because it's got an IP address, it's actually right now, it's not hooked up to my computer, it's actually hooked up to the switch and to the wireless router in the room. So actually, if you want to, Daniel, if you would, you can, I think you can start up the robot here and use the user interface to start it from your phone, if you can find it. So go into Application Web up above.
Yeah. It says a message invalid when first active.
Yeah. Okay. Give me just a second. It should be connecting. A little bit hard to read on this interface. It's homing. You can see the gripper is homing. So you're doing this from your phone, yeah?
Yes.
Yeah.
Invalid when click active.
Yeah. Give me just 1 second. We'll fix that. rotates, and it's just going to move back and forth. And this is running in a safe way, so I can let it, bump me, like if I had my hand in the way. It doesn't hurt, doesn't break my hand. And the nice thing is that it'll go back to doing what it was doing. There you go. So I'm going to stop it for now. We'll go back to the presentation. So that was just to show you how it works in terms of the web interface, that you can actually interact with it from a computer, a phone, an iPad. It makes it very, very simple to use on a factory floor through your internet. Something else that's actually really nice about the robots is that they can be put into free mode, which means that I can just move it very easily by hand. You can see that because of the low gear ratios, it means that I can teach positions and move the robot very easily by hand. I would also mention that the robots can also be mounted on a very long linear track, and that allows the robot to access a very large area. Let's say, for example, you had 3 or 4 different operations that needed to take place. You just wanted to use one robot. You could put the robot onto a linear track and it would be able to access all those different locations. So this is an example video of how that would look. This is a very tall version of the robot on a slide, on a linear slide. So you can see how it moves, how it would work. So one of the things that's really unique about this robot is you can see that a standard industrial robot, it has this big top to it, and it has to change how it gets from one side to the other, going from left to right. You can see that our robot passes underneath, and this is actually a great feature because it means that you can use it in a really small spot. Just like a human being, if you needed to work very close, you'd want to be able to have your robot do the same thing. The other thing is, this is very similar to a human arm, right? If you look at it, there's a shoulder, there's an elbow, and then there's a wrist and a hand. So it's very much like if you needed to reach into a set of shelves, just like are happening here in these videos, you can see how easy it would be for the robot to reach into the tight spaces. That's not necessarily true for a lot of other cobots that are made to be very large. So let's talk about collaborative robots. So collaborative robots are by nature they have come out of research and development and universities, and so you can see that there are some of them. All the ones over here in this corner here, they look like a man, right? They've got a cute little face maybe, and they've got 2 arms, and that's very complex. But that's not necessarily what you need to just simply pick up and put down, say, cosmetic jars, right? So that's a very expensive way of trying to replace a human, when if all the human being has to do is pick something up and put it down, then you're overpaying for what you need. So that's part of the reason why you'll notice that our robots are very different. You can see here up in the upper left-hand corner that our robot looks very different. It's very simple, and it's relatively low cost. So, as an example, I like to speak to some of our competitors. You can see here that the robots don't stop easily. And when I run this again, you're welcome to come up and see how the robot stops. The reason why this robot doesn't stop easily and why it's not easy to move is because it uses very high gear ratios. And very high gear ratios means, just like we talked about in the car, it can generate a lot of force. It can go really fast. And that's not such a good idea when you're trying to be collaborative and around people. Remember, force equals mass times acceleration. So the faster the robot goes, the more force it can actually generate. The other thing I like to point out here is you can see that, someone's putting out their hand and really trying to stop the robot. You saw how easily I stopped this robot, and that particular robot is not necessarily stopping very easily. In fact, it's taking a lot of force and it's still not stopping. So there are so this particular company is called Universal Robot. Any of you heard of Universal Robot before? Maybe. I know that you gentlemen know ABB. ABB makes something called a Yumi with 2 arms and 2 hands, and it's very complex, which means that it's not only is it very expensive, but it's kind of hard to program. It takes a lot of time and effort to make sure that the robot can do what you want it to do, versus just programming something over the web and maybe changing a couple of values. So these are examples of robots that are they're collaborative, and in this particular demonstration, this is a KUKA robot made by what is now used to be a German company, is now a Chinese company. KUKA actually makes this particular robot that they call the lightweight arm. You can see he's having to grab 2 hands rather than just one to be able to teach the positions. But more importantly, this is a very expensive robot. It's double to triple the cost of our robot. And the reason for that is that if you look at the robot, it has lots of different joints, and it's big. It's really big. And so in order to actually do something useful in a factory, you don't need all this. In order to actually make an application work, I do like the fact that he made the application work very quickly. I think that we would be able to do something very similar at half or a third of the cost. You can see that it picks it up, puts it down, that's it. If all you're going to do is pick something up and put it down, you could do the same thing with this robot, right? So that's the idea. There's also the world's largest robot manufacturer, FNUC. They do make these green robots that are supposed to be collaborative. Now, you can see this robot handles 35 kilograms. That's a lot of mass. So you'll notice that this robot doesn't go very fast. It doesn't go very fast until, I'll point out the point in the video, but here in about 10 seconds, you'll notice that the robot, when it's moving slow here, but watch as they speed it up. You see how they sped it up because they didn't want you to realize that the robot's going so slow the entire time. The other thing is that it's a big robot, and so in order to push it around and to be able to train it by hand would be very difficult. In fact, we'll skip to that piece where he's going to show you that there's some foam, but then he's going to try and push it and move it around, and you'll notice that he has to really put his entire body weight into pushing the robot around. Sorry. There we go. There's the bump. And you can see as he's pushing it, he's got to really put a lot of, can't move it fast, right? Can't move it easily, and has to put his whole body weight into it. Again, that's because they're using really high gear ratios, and the robot's built to carry 35 kilograms, so it has to be big. That's not the idea behind collaborative robots. The idea behind collaborative robots is to, basically do what a human being can do, and most human beings aren't carrying around 35 kilograms all the time. So as an example, you saw some of these other robots move, and this is an example of how our robot might move. can see that it can place a PCB into the tester, can close the lid, a test can take place, then it can open the lid, pick up the board, and put that PCB into, let's say, onto a conveyor or something. So you can see it moves very smoothly, very easily. That's the idea behind it, at least. Now, in terms of where collaborative robots can be used, collaborative robots can actually be used in many different markets. They can be used in medical devices, plastics and rubber, electronics. We even have a lot of customers who are in the medical device industry, in the medical industry. So it really depends. Really, the thing to look for are places where people are still doing some simple work that can easily be replaced by a robot that does the same thing. So this is the use of robots by market. And as you can see, the largest, the market with the largest use of robots is the automotive industry. Now, robots are also used heavily in electronics, and they're also used in metal fabrication. So the idea here is that some of the other areas like food processing and pharmaceuticals and cosmetics are going to grow as robot users because of collaborative robots. So these are some examples of how our robot might be used in, say, medical products to do testing. This is an example of something done by hand. Somebody just picks something up and puts it into a nest, and then it's ready to continue the process. Easily done by a robot. You can see here a person's just putting parts onto a pallet